guys, nice to see you. How are you doing? How was the fall break? Yeah, one more or enough? Good, nice. Back to work. So we start a new topic right now, and this will be oscillations and waves. And we will introduce periodic motion um, and try to describe quantitative periodic motion in scope of simple harmonic motion, which is the building block of any oscillation. And based on already on this derived equation for displacement of simple harmonic motion, means position as a function of time, we will introduce certain parameters like velocity and acceleration of this simple harmonic motion, and also period and frequency of simple harmonic motion. So that's our plan for today. Uh, so let us first give the definition of periodic motion. So this is some repetitive motion of an object which comes back to a given position after some fixed time interval. So there is some time interval, it passes, and this object comes back to the given position again and again, repeatedly. So that is the definition of periodic motion. And there is also some definition for simple harmonic motion, like the simplest oscillation, type of oscillation. So in that case, this acceleration of the object should be proportional to displacement and oriented in opposite direction to the displacement. Now, taking this into account, any suggestions what system would it be possible for us to consider in order to derive this equation for simple harmonic motion? So where would we have acceleration of an object proportional to its position or displacement, and its direction of acceleration should be opposite to the displacement direction? Hmm? Well, that is one of classical examples of periodic motion, but we will introduce this system a bit more in details later. However, there is one system which we already mentioned several times and considered in our examples, which satisfies these requirements. Huh? Spring and a block. So block attached to a spring, we neglect with friction, then we have spring force, which always tries to pull the object back to the equilibrium condition, means that the force and thus acceleration will be in opposite direction to the displacement, and the force, means again acceleration, will be proportional, linearly proportional to the displacement. The larger displacement, the larger acceleration. So let us now make it more visible with some drawing and introducing equations which can describe this type of motion. So let us introduce here a string block system in some excited state. Means that here we have our axis x. This will correspond to equilibrium position. This will be x equals 0. So then assume that we push this system to some excited state with displacement a. We can explicitly show that it's positive. Plus doesn't look nice. So this block possesses some mass m, and the string is described by string coefficient k, which tells us how stiff this string is. Uh, Now let us assume that this position, when it stays, the block stays at position at coordinate plus a, uh, is time equal 0. So we start from this extreme position. So a obviously will stand for amplitude displacement, like maximum displacement, which will happen in this given experiment. So what with string force? We have string force, which tries to push this block back to the equilibrium condition. So this will be F string. Um, Now let us see what will happen if we let this system go by itself. So this block will start to move to the left. So it will reach equilibrium condition. So here Fs will be equal to what? 0, because we don't have any displacement at equilibrium condition. And obviously it will not stop here. So it will continue because we don't consider any friction so far. So we don't have dissipation of energy. Kinetic potential energy transforms to kinetic and then transforms back to potential energy. So that means that this string will be constrained, and our block will move to another extreme position, which will be minus a. So let us make it clear at the beginning with potential and kinetic energy. At t equals 0, what will be about potential energy? It will be maximum. What about kinetic energy? 0. There is no kinetic energy. That's good. So then when it passes the equilibrium condition, it will be in the contrary. We will have maximum kinetic energy and minimum, like 0 potential energy. So that keep in mind. Later we will address this again. But now we kind of describe the system. Let us write expression for the string force. F s will be equal to minus k times x. That we know. And also what we can write for string force, that it will be equal to a times m. A stands for acceleration of the block times mass of the block. We neglect with mass of the string. So in this case, we can write that a is equal to minus k over m times x. So again, let us recall definition of simple harmonic motion. We said that it should be proportional to displacement and aligned in opposite direction to displacement. So that is exactly what we have here. We have linear proportionality, like to displacement, and this acceleration is in opposite direction because we have this sign minus. So with this, we can proceed further if we recall how else we can define acceleration. So what is acceleration by definition? Instantaneous linear acceleration. Okay, that's valid statement. So we can write that this will be first derivative of velocity over time, and it can be also expressed as second derivative of displacement over time. So it will be d square x over dt. So now we can substitute this expression for a, for acceleration. So it will be d square times x over dt, here is square, is equal to minus k over m times x. Now let us move everything to the left side of the equation. Will be d square x over dt squared plus k over m times x, and that is equal to 0. So this is the differential equation which gives us information about the function which describes position versus time, our displacement of this block versus time, because we measure it with respect to equilibrium condition, which corresponds to position equal x equals 0. This is second order linear differential equation. I'm sure you will solve many like this in the near future within like your math classes. Probably so far you haven't yet worked with them, but here we will try to show step by step what is the approach to solve this type of equation, so you have understanding how we come up with the final expression for this function. X is a function of t. But those who are not so much interested can consider only the final solution, because that will be sufficient for you. But probably someone is also interested to see how we come to this solution. So when we have second order linear differential equations, the way how we approach is kind of commonly accepted approach to solve these equations. We want to set so-called characteristic equation. And in this, how to set this characteristic equation, we consider that the function itself, which we want to get to know, that stands for unity, and first derivative over some independent variable for this function will stand for, let's say, some lambda. So now let us look at our equation and write this characteristic equation, like from differential equation. So we have second derivative, means we have lambda squared plus k over m. So x stands for unity, so we don't write here anything. And that is equal to 0. So this is so-called characteristic equation for this differential equation. Now, any suggestions? Does it look like something for you? What you are familiar with? What type of equation is this? Quadratic equation. So what will be the general form of quadratic equation? We can write a times x squared plus b times x plus c, and that will be equal to 0. So in our particular case here, we have a equals to unity, b equals to 0, and c is equal to k over m. So now our goal now to get solutions for this characteristic equation and see how this solution, what is the form of these solutions. Based on the form of solutions of this characteristic equation from tables, we can define what will be the form of solution for our differential equation. So that's a commonly accepted approach. Just don't ask me why there are those relationships between forms of solutions. That will be in the scope of your math class. Here we just apply quite established approach, and you can always find these relationships in textbooks or some tables. So now we solve the characteristic equation. And what we do, we need some differential discriminant of differential equation of this quadratic equation. So it will be b squared minus 4a times c is general expression. Then what we have 0, because b is equal to 0, minus 4, a is unity, and c is k over m. So here will be k over m. From here we get that our discriminant will be minus 4 times k over m. Now we go for solutions of this characteristic equation. Since it's quadratic equation, we get two solutions. We get lambda 1 and 2. And that will be equal to minus b. So in general form, let's write it. Minus b plus minus square root from the discriminant divided by 2a. So this will give us 0 plus minus square root of minus 4 times k over m, and divided by 2 because a is equal to 0 to unity. So we end up here with plus minus 2 square root of minus k over m divided by 2, can cancel out these 2, and finally we have plus minus square root of minus k over m. So as you see, we have a bit not trivial solution here because we have minus under square root. So we need to deal with complex numbers, and we need to introduce a complex unity, which is I equal to square root of minus unity. So with this term I, we can keep this in mind. We can give the final solution of our characteristic equation. That will be plus minus I times square root of k over m. So we get two equal by magnitude but opposite by sign complex solutions, like complex numbers, which are solutions of our characteristic equation. If you check in these tables for solving second order linear differential equations for these conditions of solution for characteristic equation, you will see that the general function, which will be considered a solution for our differential equation, will look like following. So it will be c1 times cosinus square root of k over m times t plus c2 times sinus square root of k over m times t. So that is exactly what we want. We want to get this displacement as a function of time. However, we still don't have it. We have only the form of the final solution, but here we have these two unknown constants. And we need to get these constants. So any suggestions how we approach this? If we have unknown constants in our equation, can you repeat, please? Well, not necessarily, but that could be considered partially as system of equations. But when we deal with solutions of differential equations, in order to get the final expression for the function, we need to apply boundary conditions. So what boundary conditions we can apply to this system? Let us take a look here on our figure. So what do we know about the system? When means we need to know time and position. Let's say we need to know two parameters, time and some other parameters. So first case, we know that at t equals to 0, position is a. So let us take this into account and consider what it will give us. So here we write that t equals to 0 and x is equal to a. So this is our boundary condition. Let us substitute this. So in the right side of equation we will have a. That is equal to c1 times cosinus square. Oh, wait a second. Before we apply this boundary condition, we make one more substitution in order to make our equations less bulky. So we will introduce omega, which is equal to square root of k over m. So as you may already guess, omega stands for angular frequency of this simple harmonic oscillation. So we can rewrite this equation. So it will be x as a function of time will be c1 times cosinus omega t plus c2 times sinus omega t. Now we want to get the unknown c1 and c2. So we consider this boundary condition, t equals to 0, x equal to a. So we have a in the left side, then c1 times cosinus omega times 0, because t equals to 0, plus c2 times sinus omega times 0. So here, sinus 0 will be 0, cosinus 0 will be unity. That means from this condition, we can write that C1 is equal to capital A. So C1 stands for the amplitude value of displacement. Okay, so that is first constant. However, we still don't know anything about this second constant. So we need to set another boundary condition. And any suggestions what it can be? Um, that let's come back again to this figure. That, well, there are two conditions which kind of relevant for interest. However, keep in mind that I mentioned that we need to know position and time. At current moment, we don't know when our block will reach these positions. Don't know at which time t block will be at equilibrium or extreme negative displacement. So what we know that at t equals 0, it stays here at extreme positive displacement. So we already applied this displacement, this boundary condition. However, if we think about it, we can get one more boundary condition from this known position in given moment of time. After the one period? Huh? After the one period? Well, after one period, it will be back to its position, yeah, but it will not give us the boundary condition to get C2. So it's not only about position. You can set this condition, boundary condition, about other parameters. So what other parameters we know about this block at extreme position? Hmm? Well, acceleration, but that's a bit too far. What is between position and acceleration? Velocity. So I mentioned you that specifically highlighted that in this position, potential energy is maximum and kinetic energy is equal to 0. If kinetic energy is equal to 0, then what is with velocity? 0. Is also equal to 0. So we have second boundary condition. We can consider now one more boundary condition, which will be the following. At t equals 0, velocity is equal to 0, and velocity is first derivative of displacement over time. So means that we, in order to apply this boundary condition, we need to take first derivative over time of this general solution, this equation, and set it to 0 at t equals 0. So that will give us an option to determine another constant. So let us do it. dx over dt will be equal to, what will be derivative of, so let's look here when we have omega already. What will be derivative of cosinus? Minus sinus. Okay, so here will be minus C1 times sinus omega t, and here we multiply by omega because we need to multiply by derivative of the argument of the cosinus. Then we have plus C2 times cosinus omega times t, and here will be times omega. Now, when we want to set this boundary condition that it will be equal to 0, we need to set here t equals 0. So what we have, sinus 0 will give us 0, and cosinus 0 will give us unity. So we can write here that in order to get 0 in the right side of the equation, C2 should be equal to 0. Because omega is not equal to 0, cannot be equal to 0. Then we don't have any oscillations. So now we have C1 equal to amplitude A and C2 equals to 0. So we can write the solution for differential equation considering our specific condition when initial position of the block is positive A at t equals 0. So our position or displacement as a function of time will be A times cosinus omega t. So that is solution for specific condition which is described here in our figure. However, it's possible that the block at t equals 0 will be not at A, but at some arbitrary position x. So in order to take this into account and have a general solution, we can introduce so-called phi, phase shift, and add it to the argument of cosines. So the general solution for x as a function of t will be A times cosinus omega t plus phi. And this argument of the cosinus will be the phase of the oscillation. So let us show how it may influence the function. So in order to do this, let us draw displacement versus time. So if we have phi, for instance, equal to 0, then we have our case which we described. Initial moment of time, t equals 0, displacement is equal to positive A. So it goes like this, and then we have this periodic up and down. So that's how displacement will change with time. However, if, for instance, we get phi equals to pi over 2, so it will be phase shift, and that will result in initial position x equal to 0. So then it will look like following. It will just go down to the same amplitude, and it will go with the same frequency, but shifted by the phase of pi over 2. So amplitude is the same as you see here, but initial condition will be different. So it starts not from x equal to plus a, but x equal to 0. So in order to adjust our equation to any initial condition, we can change this initial phase shift phi in order to satisfy our equation to the given conditions of the experiment. So now, if we have function of displacement versus time, we can also get velocity and acceleration versus time, which are also very important parameter for describing this oscillation, simple harmonic oscillation. So velocity is first derivative of position over time, and that will be minus omega times amplitude times sinus omega t plus phi. So in order to get acceleration as a function of time, that will be first derivative of velocity over time minus omega square times a times cosinus omega t plus phi. So here we see that both, let's say, all kinematic parameters, means position, velocity, and acceleration, are functions of time, and what is the most important are periodic functions of time, because we have these sinus, cosinus functions. And we can take a closer look here at these prefactors before the periodic functions, and that will correspond to maximum values of velocity and acceleration of this simple harmonic motion. So we can write that V maximum will be equal to omega times A. And now let us recall the substitution which we made previously. You see, the general solution was cosine of square root k over m. So in order to make it less bulky, we made a substitution which gives us, like, introduces omega, which is equal to square root of k over m. Now we can come back to this. So we can write here that omega is equal to square root k over m. So we can describe now this maximum velocity of the block in terms of parameters which describe features of the block and string. So means we have string coefficient and mass of the block. So here we can write square root k over m times amplitude value, amplitude displacement of this block. And similar we can do for maximum acceleration. So it will be omega squared times a, and that is k over m times a. So these are the parameters which are, like, let's say, kinematic parameters for periodic simple harmonic motion. Also, we need to introduce period and frequency of this periodic motion. So let us come back to the beginning where we gave the definition of periodic motion. So that is the repeating motion, which, like repetitive motion, which results in the that this body which follows this repetitive motion comes back to the same given position after a fixed interval of time. So every fixed interval of time, it will come back to given the same position. This fixed interval of time is nothing else as a period of the oscillation. And taking into account this condition, we can write that what does it mean that the system will come back to the same point or in the same position again? So the phase shift, or like phase difference between initial position and after this fixed interval of time should be different by 2 pi. Means it makes this full circle, and comes back to initial um, position. So we can write it as following. So we have omega times t plus capital T, which stands for the period of oscillation, plus phi, which is initial phase shift, not equal, minus um, omega times t plus phi, so we can put it in parentheses here. That should be equal to 2 pi. So the difference between phases of oscillation after fixed interval of time, which is equal to period of oscillation, should be equal to 2 pi. And that means that position will be the same, but the phase shift will be 2 pi. So now if we open this parenthesis here, we will get that omega times capital T is equal to 2 pi. And from here, you can write that period of oscillation is defined as 2 pi over omega. So we keep in mind that omega is equal to square root of k over m, and eventually we will get 2 pi square root of m over k. So that is the equation which gives us period of simple harmonic oscillation of the system block string, which is defined by the properties of the block, the mass of the block, and the string, its stiffness, which is quantified by string coefficient. Now, tell me, what is the relationship between period and frequency? Yes, so frequency is 1 over period. So with this, we can write that it will be 1 over 2 pi times square root k over m. And obviously, probably you remember the relationship between angular frequency and frequency. So angular frequency is 2 pi times frequency. Now, if we multiply this expression by 2 pi, we will see that omega is equal to k over m, which actually what we initially considered during derivation of our equation, this substitution. So that is expression for angular frequency. And pay attention here that angular frequency is completely defined by two parameters, which is stiffness of the string and mass of the block. However, when we have, let's say, linear velocity and acceleration, here we also need to take into account how far we move this string block system out from equilibrium condition. So, so angular frequency is actually a feature, intrinsic property of this system, but these guys, they are not, because they also depend on the displacement, initial displacement, which was provided to the system. So, summarizing our discussion today, we introduced periodic motion, and the most simple example of periodic motion is simple harmonic oscillation. So definition of simple harmonic oscillation, it tells us that acceleration of the system, of this, let's say, body, should be proportional to displacement and should be aligned in opposite direction to the displacement. So means if we consider again here our block string case, we see that acceleration of this block is proportional to displacement and opposite in direction. So that is perfect satisfaction of these conditions for simple harmonic motion. That's why we can consider this system as an example of simple harmonic oscillator. And then we came up with the second order linear differential equation, which gives us information about x as a function of time, so position as a function of time, or displacement as a function of time. We introduce this characteristic equation based on this differential equation, solve this characteristic equation, where is this? Next a bit lower. Got the solution, which is a complex number, but according to this type of solution and form of solution for characteristic equation, we can find in tables the equations which satisfy the solution of our second order linear differential equation. When it is the characteristic equation has equal by magnitude but opposite in size complex numbers as solutions, then the form for solution of our differential equation is this. So you can find it tabulated for the ways how second order linear differential equations are solved. So now we introduce this omega as square root of k divided by m. We introduce two boundary conditions. So first one was when we define C1, it's a little bit higher. Yes. So first boundary condition was at t equals 0, x equals a, is maximum displacement, positive displacement. We could not consider any other positions, 0 or minus a, because we didn't know time. Time was not given. We didn't know at which moment of time it will reach this position. So we had to stick to this time equals 0, but we could also claim that velocity at this moment is equal to 0 because kinetic energy is 0 and potential energy is maximum. So velocity is given as first derivative of displacement over time, so we apply this condition, second boundary condition, to first derivative of our general solution, and get the expression also for like value for second constant, which is equal to 0. So eventually we get the final equation which describes harmonic oscillation and introduce this phase shift p in order to make it in general case, not only for specific case when initial position is positive a, it can be anything at t equals 0. And based on that, we introduce maximum velocity and acceleration and period and frequency of simple harmonic motion. So with this, we finish our discussion today. We will proceed further with simple harmonic motion and introduce kinetic and potential energy as a function of time and so on. So thank you very much for attention and see you next time on Wednesday.